Welcome to this explainer. I'm your host, and today we are going to build a deep, truly logical understanding of electrostatics step by step. Just imagine we're sitting side by side with a fresh, clean notebook right in front of us. We aren't here to blindly memorize formulas, right? We're here to understand the actual physics of the universe at a fundamental level. So let's get into it.
Okay, let's kick things off with the simple observation. We've all seen sparks flying off a sweater when we take it off in dry weather. Or, witness the incredible power of lightning during a storm. You've probably even done that classic trick where you rub a plastic comb on your hair and use it to pick up tiny bits of paper. But what exactly is happening there at a fundamental level? Why do these seemingly neutral objects suddenly exert this mysterious pulling force?
Well, here is our roadmap for today's explainer. First, the basics of charge. Second, conductors and insulators. Third, core properties. Fourth, Coulomb's law. And finally, the superposition principle.
All right, let's jump right into Section 1, the basics of electric charge. Through years of really careful experiments, scientists determined that there are actually only two kinds of electric charge. Benjamin Franklin was the one who named them for us, positive and negative. And what's absolutely fascinating here is that electrification simply comes down to the transfer of a tiny, tiny fraction of electrons during friction. So when you rub a glass rod with silk, the less tightly bound electrons in the glass literally jump over to the silk. The glass loses electrons, becoming positive, and the silk gains them, becoming negative. Absolutely no new charge is magically created, it's just being moved around. And the golden rule here, the one you always need to remember, is polarity. Like charges repel, and unlike charges attract.
Now, since we obviously can't see these electrons moving with our naked eye, we need a tool to detect them. Enter the gold leaf electroscope. It's a remarkably simple device, just a vertical metal rod inside a box with two incredibly thin gold leaves attached to the bottom. When you touch a charged object to the metal knob at the very top, the charge flows straight down that metal rod and spreads onto both gold leaves. Because both leaves receive the exact same type of charge, what do? They repel each other. As the charge flows down, the gold leaves diverge based on the magnitude of that charge. The wider they split, the greater the charge. It's brilliant.
Moving on to Section 2. Conductors and insulators.
So why does the metal rod in our electroscope let the charge flow so easily, while the glass rod just holds onto it? Well, it all comes down to internal structure. Conductors, like metals, human bodies, and the Earth, have electrons that are comparatively free to move around inside the material. Insulators, on the other hand, like glass, nylon, or plastic, offer very high resistance to the passage of electricity. So the crucial takeaway is that putting charge on a conductor distributes it over the entire surface almost immediately, but on an insulator, the charge stays exactly where you rubbed it. This is exactly why you can build up a charge on a plastic comb held in your hand, but not on a metal spoon, because both your body and the spoon are conductors, and the charge just instantly leaks away right into the ground.
Okay, Section 3, core properties of charge.
You're going to want to remember these three rules, the three pillars. First, additivity. Charges add algebraically, just like regular scalars or real numbers. If you have a system with a +2 charge and a -5 charge, your total net charge is simply -3. Easy enough. Second, conservation. The total charge in an isolated system is always conserved. You can redistribute it all day long, but you can never create or destroy net charge. And third, charge is always quantized.
Let's pause and look a bit closer at that third pillar, quantization. The formula we use here is Q equals N times E. This is just a basic, fundamental law of nature. All free charges are integral multiples of a basic unit. Basically, that means charge is actually grainy. It's not continuous. That basic unit, E, is the magnitude of charge on a single electron or proton, which is roughly 1.6 times 10 to the -19th coulombs. And N is an integer. You can have exactly 1 electron or exactly 2 electrons, but there's no way you can ever have 1.5 electrons. Now, at a macroscopic scale, like when you're reading a meter in an experiment, the charge looks perfectly continuous. It's a lot like how a pile of sand looks completely smooth from a distance, right up until you zoom in and see the individual grains.
Now for the core mathematical derivation, Section 4, Understanding Coulomb's law.
I'd like to introduce you to the French physicist Charles-Augustin de Coulomb. Back in 1785, using a highly sensitive instrument called a torsion balance, Coulomb actually managed to deduce this relationship without even knowing the explicit magnitude of the charges he was testing. It was pure logic. He cleverly used identical metallic spheres to divide charges in half symmetrically over and over again. This allowed him to precisely measure how the pushing and pulling forces changed with different amounts of relative charge and at different distances.
Let's trace his logic step by step.
First, his experiments proved that the electric force is directly proportional to the product of the magnitudes of the two charges. Basically, more charge equals a stronger push or pull. Second, the force is inversely proportional to the square of the distance between them. Meaning, if you simply double the distance separating the charges, the force doesn't just halve, it drops to a mere 1/4 of what it was. It falls off exponentially. Finally, we combine these two observations with a constant of proportionality, which we just call K.
So bringing it all together, we get this final crucial formula, F equals K times Q1 times Q2 divided by R squared. Now, for convenience in more advanced physics, K is often written out as 1 over 4 pi epsilon naught. And that epsilon naught, that represents the permittivity of free space. Make no mistake, this simple equation is the absolute bedrock of electrostatics.
Now please pay close attention here because a very, very common exam mistake is completely ignoring the vector nature of this force. Force is not just a number, right? It has a direction. The electrical force between 2 point charges always acts directly along the straight line joining those two charges. So whenever you solve a problem, always, and I mean always, draw an arrow on your page first to verify the direction of repulsion or attraction.
Which brings us perfectly to Section 5, the superposition principle.
Take a second to think about this logically. If our main formula, Coulomb's law, only works in isolated pairs, just Q1 and Q2, how on earth are we supposed to solve a complex system that has dozens of interacting charges, all pushing and pulling at the exact same time? Does the sudden presence of a third charge somehow mess up or interfere with the force between the first two?
Well, the brilliant solution is found in the principle of superposition. Experimentally, we find that the force between any two individual charges is completely unaffected by the presence of a third charge. They are totally independent interactions. So what do? You just calculate the force for each pair individually using Coulomb's law, and then you just add them all together using vector addition. It is simply the vector sum of all the individual forces.
Before we completely wrap up today's explainer, let's do a quick review of our exam strategy notebook. Number 1, never solve blindly. Understand the core concept before you try memorizing the formula. Number 2, always draw your vector diagrams first so you can visually see exactly which way the forces are acting. Number 3, check your units carefully. Remember, we often deal with microcoulombs, which means 10 to the negative 6 coulombs. And finally, for superposition questions, just break the problems into smaller parts. Calculate pair by pair, trust that step-by-step logic, and then apply your vector addition. All right, I'm going to leave you with this final thought-provoking question to really test your conceptual clarity. We established earlier that charge is strictly conserved. Yet, in certain subatomic processes, nature literally turns a single neutral neutron into a positively charged proton and a negatively charged electron. So, did nature just break its own conservation rule? Think about the total mathematical charge before and after that reaction actually occurs. Thank you so much for joining me for this explainer, and remember, keep thinking deeply.